Chapter 5. And this will be the last chapter for the 141 class. So first off, composite functions. So you have in terms of fog, which is the f of g of x. And then you could have goff, which is the g of f of x. So, for example, if f of x is 1 over x plus 2, and g of x is 3x, then fog. So I start with the f first. Everywhere I see the x, I plug in g of x. So this will be 1 over 3x plus 2. And then if we do goff, so now we start with the g. Everywhere we see the x, we plug in the f of x. So this will be 3 times 1 over x plus 2. And this will give us 3 over x plus 2. So composite functions. Other things they talk about is you get in terms of one-to-one function. So a function is one-to-one if for every x only one y, and for every y only one x. So this one, in terms of a graph, has to pass both the vertical and horizontal line tests. So we'd have to pass both of these for it to be one-to-one. So if you think in terms of graph, so if I had a graph something like this, and so I had this curve, that graph would be one-to-one. It would pass both the horizontal and the vertical line tests. Now then we get to inverse functions. So if I had y equals 2x minus 5, and I want to find the inverse of this, so about what I have to do here is just flip-flop the x and the y. And so now we're going to have x equals 2y minus 5. And then I can solve this for y. So add 5. Add 5. So x plus 5 equals 2y. And then we could divide by 2. And we get that y equals x plus 5 over 2. So we had our f of x. Our f of x was 2x minus 5. And now we have our inverse, f inverse of x, which is x plus 5 over 2. All right? And the way you can verify if indeed you have the inverse is that this, if you do the f of f inverse, you should get 1. And if you do the inverse of f of x, you should get 1. All right? So, for example, in the terms of one I just did, if I do f of f inverse, we would have, this is going to be 2 times the x plus 5 over 2 minus 5, which will be x plus 5 minus 5, and we get minus 5, sorry. I need to make a couple changes here. So this should be get x, not 1. Sorry about that. That should be x. And let me change this. This should be 5. So x plus 5 minus 5 will give us x. So indeed we do have the inverse. So the other thing about inverses has to do with their domains and the range. And that is the domain of f becomes the range of f inverse. And then the range of f becomes the domain of f inverse. So inverses. Well, then the chapter talks about exponential functions. So something in this form, f of x equals ca to the x. Exponential. Right? So my basic exponential being y equals 2 to the x. And if I were to graph this, you see the graph is going to look something like this, right? And so my domain is negative infinity to infinity, and my range is 0 to infinity. So my exponential functions. So if I had a problem and I want to solve it, so let's say I had this one I want to solve, we got 3 to the x plus 1 equals 81, right? But 81 I can rewrite as 3 to the 4th. So we got 3 to the x plus 1 equals 3 to the 4th, which of course would then mean that x plus 1 would have to equal 4. And so we could subtract, and we get that x is going to be 3. The other types of thing you'll see is given an equation. So given d of h equals 5e negative 0.4 times h. And if I set h is equal to 1, we should be able to solve this. This would be 5e to the negative 0.4 times 1. And this will give us 3.35. So exponentials. Well, the opposite of exponentials then are logarithmic. And in terms of logarithm, you have 2 buttons on your calculator. You have an log button, which is log base 10. And then you have an ln button, which is log base e. Right? And if we look at a graph here, so let me draw my exponential. So let's say this is my graph, y equals 10 to the x, right? And now if I draw my logarithmic graph, it looks like this. Y equals the log of x, right? And again, if I look at these and I say, okay, well, the domain here is negative infinity to infinity, and the range here is 0 to infinity. I come to the one in green, and we find here that the domain is 0 to infinity, and the range is negative infinity to infinity. So these are inverses of each other. The other thing about inverse functions is they are symmetrical with regard to the line of y equals x. Right? So they're symmetrical about that line. Right? Well, we can change from log form to exponential form. So log base A of x equals y would be a to the y equals x. So if I had something like this, that 3 to the 4th equals 81, I want that in log form. Well, this would be log base 3 of 81 is 4. And then conversely, if I had the log base 2 of 8 is 3, well then in exponential, this would be 2 to the 3rd power is 8. So then given a problem, we can be able to solve it. So if I had something like this, log base 3 of 4x minus 7 equals 2. Well, this would be then 4x minus 7 is equal to 3 squared. 4x minus 7 equals 9. Add the 7. So 4x equals 16. And then we could divide. And we get our value of x. So x is going to equal 4. Well, then in terms of properties of logarithms, there are several they talk about. So properties of logarithms. So we have the product rule. Log base b of m times n is the log base b of m plus log base b of n. Right? Next one is the quotient rule. Log base b of m over n is the log base b of m minus the log base b of n. And then we have the power rule. Well, the log base b of m to the p is p times the log base b of m, right? Are the rules, right? And then a couple other statements, and that are these. And that is if m is equal to n, then the log base b of m has to equal the log base b of n. Right? And then the other one is if the log base b of m equals the log base b of n, then m has to equal n. So all those rules and those statements come in handy later when we go to solving these things. So in terms of how those three rules work, product, quotient, power rule, get a question like this where we want to expand the logarithm. So log base 3 x plus 2 squared times x over x minus 7 cubed. Right? So this is going to be 2 log base 3 x plus 2 plus the log base 3 of x minus 3 times the log base 3 of x minus 7. So we used our power rule, our product rule, and then our quotient rule. And then, of course, can do this going the other way, and that is now write as a single logarithm. So given 4 log base 5 of x, 3 log base 5, x minus 9, minus, and over here, 2 log base 5, x plus 12, plus 3 log base 5, x minus 11. Right? So we know it's going to be log base 5. Right? And my fraction bar, everything to the left of the fraction bar is on the top. So on the top we have x to the 4th, and then x minus 9 cubed. On the bottom, we have x plus 12 squared, and then x minus 11 cubed. And we end up with the. Well, then the other thing we can do, again, we said on your calculator, you will only have an log key and an ln key. What do you want to do the log of something else? So let's say I want to know, in terms of being able to take a log of some other base. So there's this thing called the change of base formula. So the log base b of m is the log of m over the log of b, or the natural log of m over the natural log of b. Okay. So, for example, the log base 12 of 29875. Okay. This is going to be the same as the log of 29875 over the log of 12. And if you plug that in your calculator, you end up giving, when we're going to round here, we get 4.1469. Rounding my answer to that many places. Right? Let me just check that. Log of 29875. All right. 4.1469. And we can check to see how close this is. So now if I do 12 and I raise it to this power, I should be in the ballpark of that number. And given that I rounded, we end up here 29871. You know, if I took a few more places, my answer would be even better. Right? So solving a logarithmic question. So given something like this, log base 3 of x minus 2 log base 3 of 5 log base 3 x plus 1 minus 2 3 of 10. Well, this would be log base 3 of x over 5 squared equals log base 3 of x plus 1 over 10 squared, right? Which means that x over 25 is going to be x plus 1 over 100. Again, that's because if the log of m equals the log of n, then m had the equal n. And so we could solve this. So this would be 100x equals 25x plus 25. And we could solve this. Subtract 25x. And so 75x equals 25. And then we could divide. And we get x is going to equal 1/3. Oh, let's see, another types is like this. Natural log of 2x equals 5. Well, the opposite of natural log is e. Right? So e and e. So 2x equals e to the 5th. And then we could divide by 2. And so x is going to equal e to the 5th over 2. And then depending on how they want the answer, if they want the exact answer, that would be the answer. If they wanted the, in terms of a certain number of decimal places, we can plug that into a calculator and get it. Let's look at another one. So let's say you got 4 to the 3x. 4 to the 3x, and then I actually wanted this to be a plus. Plus 7 equals 112. So now I can subtract the 7. So 4 to the 3x equals 105. X is an exponent. The way we get to exponent is by doing logarithms. So I'm going to do the natural log. You could do log log. It doesn't matter either way. So this becomes 3x natural log 4 equals the natural log of 105. Okay. And then we want to solve for x, so we just divide by everything that's not the x. So I can divide this by 3ln4. Divide this by 3ln4. And we get x is going to be 1 point, and I round this one to a few places. We get that answer. Well, then other things that are exponential is you get to money. And so we have a few other equations to help us. First off is simple interest. I equals PRT. I is the interest. P is the principal. How much money did you put in the account? R is the rate. And T is the time. That's in years. Then you get compound interest. A equals P 1 plus R over N to the NT. Okay. And so here, A is the amount. So how much would you have? P is the principal. How much did you put into the account? R is the rate. N is the number of times compounded per year. And T is the time in years. And then the other type then is continuous compounding. And for that, you get this equation, A equals P E to the RT. Right? So let's just look at an example of the compound interest equation. So let's say here we have $7,000 at 3.5% compounded monthly for 5 years. So A is going to equal 7,000. 1 plus 0.035, compounded monthly, so that means 12. And the exponent is going to be 12 times 5. And you plug that in, we round this to the nearest penny, we get 8336.60. For So then you can have either exponential growth or decay. And so you get this A sub t equals A naught e to the kt. So A sub t is the amount at time t. A naught is the initial amount. K is the rate of growth, which would then be a positive number, or the rate of decay, in which case the number would be negative. And then t is the time. So let's look at an example of how this would work. So given an initial population is 200 and grows to 247 after 8 hours. And the question that is, how many will be present after 30 hours? So how do we solve this? Well, let's look at what we know. Well, we know that A naught is 200. We know A sub 8 is 247, and A sub 30 is what we want to find. So right now we don't know the K value. We don't know the rate at which it's growing, but we have enough information to find it. Because we have 247 is going to equal 200e to the 8k. So we can solve this for k. And so 1.235 equals e to the 8k. And then we can take the natural log. So the natural log of 1.235 equals 8k. And then we could divide by the 8. And we get our k value. And in this case, get 0.0264. Right? And now when we know the rate, we can answer the question, which is how much will be present after 30 hours. And so A30 equals 200 E 0.0264 times 30. And rounding this to the nearest whole number, we get 442. And then the other equation they talk about in this chapter deals with Newton's law of cooling. And so U T T plus U naught minus T E to the KT. And K is 0. So given that the room temperature is 30 degrees Celsius and we're starting at a temperature of 100 degrees Celsius, we want to answer this question, and that is if the temp is 80 degrees after 5 minutes, when will the temperature reach 50 degrees? Right? So we can first find our formula for UT is going to be 30 plus 100 minus 30e to the kt. So it's going to be 30 plus 70e to the kt. Right? Right. So now we can use what we know. And so now we have that 80 is going to equal 30 plus 70e to the 5k. And again, we want to solve this, so now we can first subtract. So 50 equals 70e to the 5k. And then we can divide. So 5 over 7 equals e to the 5k. Take the natural log of both sides. So the natural log of 5 over 7 equals 5k. And then we can divide. And if you plug that into the calculator, you get a k value of negative 0.0673. And now we know that, we can answer the question. And so we have that 50 is going to equal 30 plus 70e negative 0.0673t. And again, we're going to solve, so subtract 30. And so 20 equals 70e 0.0673t, and then divide. And so now we have 2 over 7 equals e 673t, and again, opposite is natural log. So the natural log of 2 over 7 equals 0.0673t, and then lastly we divide. And we can get our value of t. And so this time we get about 18.6 minutes. And we will be at that temperature. And that will conclude this video.